how are these neurons on this multi-electrode array playing Pong?
So essentially, I mean, when you use words like fuse together, it kind of gives you some interesting vibes. But in practice, we're able to grow cells, especially neural cells. They are evolved to connect. They're evolved to network together. And so when we place these cells on these, what we call microelectrode arrays or MEAs, which is sort of a bed of small electrodes that allow us to measure the electrical impulses of these cells as they're active and deliver small electrical pulses to the cells, they actually naturally do this. There is nothing particular, it's synthetic in that we bring it together manually, but it's not wholly artificial. It's leveraging the natural properties of these systems. And what we do then is grow these cells on these MEA, and then we have to code information and decode information. And that's where electricity comes in. Electricity is this shared language between silicon and between the biology. And so we can actually pattern the types of electrical pulses we deliver to convey information. And then we can decode the patterned electrical responses from these cells to understand how they're responding. Now, there's still a lot of work to do here, but we've been making some really interesting strides forward in figuring out the best way to do this part.
Really cool. You're a great communicator, man. Really, really clear. Let's contextualize this within the Pong system, because I think you laid it out really nicely there. Maybe people have some idea what this looks like. How are these neurons on this multi-electrode array playing Pong?
So the old Pong work that we did was actually not the simplest, but one of the simplest approaches we could have taken. When we started out, we had a lot of options. There's a huge amount of ways to go about this. And so we did what I thought at the time was the simplest idea and said, let's do the simplest ones first. And so we took the inspiration from how biology can decode the world, which is effectively what's called topographic. So for our eyes, for example, if we see something in the left of our visual field, there'll actually be a little map, topographic map, they call it, in our visual visual cortices that actually will decode it and have a one-to-one mapping. And then we took the rate, and the closest analogy for the whole system is actually a rodent barrel whisker cell, it's called. And these barrel cells have a map of where the whisker is on the animal's face. And the more you tweak the whisker, the faster it fires. And so that's what we did. So we had this map that was initially inspired by the visual system, but then we added rate to it. So the closer the ball got to the end, the faster the rate would fire. And so in the end, it ended up kind of like how a rodent's whisker would work. And then what we did was we said to the cells, we're going to put some information into one area. We're going to read information out of a couple of counterbalanced regions to make sure there was no bias. We don't want to be the case where we sort of stimulated in one area and the cells just learned to do something really simple. They had to have a bit more control over their system than that. We wanted to make sure there was no bias. And then we read out of this counterbalanced regions. And what we found was that if the cells would actually understand for the given value of cells in a dish, right? This is not understand like we would understand. They would understand like the most basic primitive systems you could imagine. What their task was, in other words, move, paddle to hit ball, they would actually change their patterns of activity to do that.
So you're encoding the particular properties of the game Pong, which is all you control in that game is actually the paddle, right? And then the reward function is, you're rewarding the neurons, which we'll get into in a bit, when the ball hits the paddle at the right angle. And then you are providing some sort of negative reinforcement or negative feedback to the neurons when the ball misses the paddle or the paddle is far away from the ball. Are those sort of the two central things that you are trying to encode and then stimulate in those neural populations?
Yeah, so concretely, there's two aspects. We encode the position of the ball relative to the paddle. So if the paddle is aligned to the ball, it gets one sort of stimulation, left another, right another. We had, in that case, 8 points where we would use to stimulate. And then we would also give it a different type of stimulation, whether it successfully hit the ball or missed it. So the setup itself was actually quite simple in that regard.
And where are you choosing to stimulate? So you have all of these plated neurons that you grew from stem cells, right? Where do you choose to stimulate them? What neurons in that population do you choose to stimulate? And how do you make that decision?
Well, in those initial cases, it was pretty arbitrary because we were growing these what's called a monolayer, which is a single layer, although they do tend to have some more structure in there, but it's sort of undirected, uncontrolled of cells. And so we looked at it. And initially, when we started out, we used to set up a specific input output relationship for every culture. And that was incredibly time consuming with the old hardware and software that we were doing. It would take literally hours to map it. And eventually we asked the question, look, if neural cells are meant to be plastic and meant to be able to reorganize their activity, why are we the ones sitting here trying to shape the input and output relationship instead of letting the cells shape how they respond? And so we then just created a very fixed pattern. We had a little area at the top that we called the sensory region. These are all cortical cells, but we called it a sensory region because we put sensation, these electrical pulses in. And we had
Right.
these counterbalance areas we call motor regions because they moved the paddle, again, all the same cell type, and we'd read activity out of. And so that was the same for all the cultures back then. With the new systems we built, the CL1, it's very, very easy to change these mappings, and you can do it rapidly, even in real time, pretty much if you want, or close to it. And so we have a lot more options now than we did back then.
The work of Michael Levin, this
Yeah, I
sort
know
of
Mike, I know Mike.
yeah, exactly. He's really informed a lot of these podcast episodes. So you could basically use
Yeah,
any human term for a neuron in a dish, and I am totally cool with that because I
yeah,
believe all these things are spectrums and continuums now, and you have to tell me
yeah,
why those neurons aren't seeing. I think that it's actually a kind of totally legitimate way of speaking about it, and maybe we can get into those differences later. But yeah, I think
yeah.
this is a completely fine way of talking about these systems.
Mhm.
So maybe it's worth talking about the reward function because this is sort of an important aspect of this, I think. Because, like, what is the dog treat analogy here? What is the you're such a good boy, hand them the treat, feedback signal happens? How are you
Mm.
doing that for neurons on a plate?
Yeah. And initially, we used the words reward and punishment. And we were using that before neuroscience, my background was psychology. And in the strict behaviorist sense, a reward is something that increases the probability that a behavior will arise, and a punishment is something that decreases the probability of a behavior arising. It has nothing to do with it being pleasant or painful or anything like that. It's simply the probability of a behavior. And cells having electrical activity is, again, one of the most rudimentary behaviors, but it is a type of behavior at the most basic level. However, again, many people misunderstood that. So we now use the words, and I think these words are more intuitive to understand anyway. They're probably better. We just didn't think about it initially. Um, we use the words now reinforcing in that it's going to keep a set of patterns happening, or plasticity inducing in that it's going to incentivize the cells to change that pattern and how it relates. So what we used initially to be plasticity inducing was based on this theory that's been worked on by many, many people. It was originally developed by Professor Karl Friston over at University College London, and it was called the free energy principle. And what the free energy principle says at a sort of at a gross oversimplification, as it is a very overarching theory and a broad branching theory at that, is that a system will try to predict its environment by minimizing what it calls its free energy, but you can also think of as a form of information entropy or the amount of disorganization. And what that basically says is that we are, and there's this part of it that calls active inference, we are going to aim to predict our environment and align those predictions with what we experience. So if I reach for my cup, I don't really, in any sort of direct sense, see the cup except in the gestalt sense. My brain interprets signals it receives from my eyes that the photons are bouncing on. And I'm going to make a model and say, it's likely this distribution of possibilities that there is indeed a cup there based on what sensory information I've seen. And if I was to engage in a particular action, like reaching for it, I would successfully pick it up. And if that happens, my expectation aligns with the future sensation of the world. it gets a little complicated, but that's the core of it: is can you predict the world? And if not, how do you then in future align it? There's only two ways. One is to get better at reaching for the cup. If I reach for the cup, I knock it over, that surprises me. It doesn't align with what I expected as an outcome. And so then I have to either get better at knowing that if I reach for the cup in that way, I will knock it over, or I have to get better at picking up the cup and controlling the world. These are sort of the two options to align.
Yeah, well explained. It's a hard concept to explain. I've spoke to Friston, and that's probably one of the best explanations I've gotten, because it's a damn hard concept to really explain simply. So I bow to you on that one. Good, nice one, nice job.
Well, he's the godfather of it, of the theory. So he has a lot of nuance that I'm sure he would, with very good grace, because he's an absolute gentleman scientist.
Yes, 100%.
We'd probably say, well, actually, Brett. but at a high oversimplification, I believe that this would be accurate. The thing is, though, if we get down to this conclusion, right, that there's really only two ways to try to get better, either better prediction or better control, we asked the question, well, what if then we made better prediction impossible? What if upon the cells doing a set of activity patterns that meant, let's say Pong, they missed the ball, we gave them something that couldn't be predicted, random white noise. Would the cells, and it was a question, would the cells then actually change their behavior to get better over time at hitting the ball? Because that's the only way they could predict their environment. If you miss, you don't know what's going to happen. It's kind of the equivalent of if I'm in a room and I do something wrong, and let's say you turn the lights off. Like over time, I'll just be like, oh, I did it wrong, and it's going to be dark for a bit. That's okay. I know that will happen. But if every time, like one time you turned the lights off, one time you played loud music, the other time you dropped me through a trapdoor, like I don't know what's going to happen. The only thing I could do is be like, all right, I better hit that ball because I just don't know what's going to happen next. Now, this is anthropomorphizing it, but you could imagine that this is true at that level of information physics as well. And so that's what we did for the cells. And what we found was actually, indeed, they did end up remarkably adjusting their activity patterns very rapidly to try and create a more predictable environment and actually control it, which meant from our perspective, not the cell's perspective, but our perspective, the cells looked like they were playing the game Pong.
So when the paddle hit the ball at the absolute perfect angle, you would give it the most patterned, predictable, lovely, gorgeous stimulation that it likes, quote unquote.
Well,
and then
it was a bit rougher than that. It was any hit would get something predictable, any miss would get something unpredictable. Again, we took the simplest approach possible.
Gotcha. So I was trying to figure out then, is there like a distribution of, okay, that exact ball hitting the paddle just 1 centimeter over is slightly worse, so then the pattern is slightly more jumbled, slightly more noisy, and then you kind of have it's not exactly that fine grained.
No, we did discuss this, and as I said, we started with the simplest approach, and essentially, like as we described in the paper, there were two simpler approaches and the one that worked quite well. And what we found is as we improved the sort of complexity, we could start to see more and more measurable effect. Now, we could have continued to go down that road, try to refine and get better and better at Pong, except we're not set up to be a Pong playing company. I mean, Pong's a cute example, but it's not in of itself what's going to really matter in the world.
That should be the big goal.
Once we'd had the effect and we showed
company.
We're not a Pong playing company, although we do see it at Pong. We realized very quickly, this is a nice effect. We can see it. Cells in a dish can indeed do some things. And we realized, but you need the foundation to do it, not just for us, but for the world. Because if we're the only ones with this technology and with access to this technology, we will make progress. But it'll be a fraction of the progress if we can bring on a community of people around the world who want to explore these capabilities with us.
Yeah. Yeah, I want to build something now. After this podcast, I'm going to try and get access to this and see what I can do, because that sounds fun.
You can sign up at Cortical Cloud. And if you look at the code of Cortical Labs, we have Cortical Cloud. And you can actually sign up and join. There's a bit of a wait list, but you can sign up and get access.
Cool. I originally came across DishBrain while preparing for my episode with Karl Friston in the first place. This was maybe 8 months ago or so now. It was the first time I came across Cortical Labs and your work. And it just blew me away. I was like, wow, that's that seems like really convincing evidence that the free energy principle is happening not just on the level of the organism, but at all of the smaller levels of organization as well. As you go down the biological hierarchy at all levels of self-organization, it seems like this principle is playing out. And this seemed like really strong evidence for that, where I hadn't necessarily seen strong experimental evidence elsewhere of this actual model prediction minimization. Like, it's a great framework, it sounds nice, but I'd never seen an experiment that was like, wow, that seems like really good evidence that that's actually what's happening. Do you think that result is one of the strongest pieces of evidence for that's what's happening at the lower levels of biological self-organization?
I think lower levels is an interesting term. And the answer is I do think that it is evidence that there is drivers, information-based drivers in this. And bear in mind, like uh, Professor Friston and I, we worked together before, on these papers. He was senior author on this paper, but we do have slight difference of opinions on these. I
Interesting.
believe that it is an informational driver, but I do believe there are others out there. And we've been working on exploring some of those drivers over time, and we'll have some work out fairly soon, putting real numbers and math behind that. But I believe that there are multiple systems running. The free energy principle in different iterations has covered the idea that there are interacting drivers, but generally proposed that this is the principal driver, which I don't find as convincing as the idea that it's one piece of a much broader puzzle.
Right.
So ultimately, though, the nice thing about the way we're doing it is we can test it. And a lot of the concern some people have with the free energy principle is that it is a principle. It's not a theory. There's a reason it's not called the free energy theory. It's a principle, and it can't really be falsified in of itself. You can test different applications of it, and that's one thing we did, and we found support for it. But as a principle itself, it's very hard to falsify it. And so we're very keen on looking at particular applications that can be falsified or supported, and figuring out how we put together a much larger picture on how these systems work.
The Giant Shoulder mission is to explore radical ideas in biology, neuroscience, and consciousness, and elevate those stories to the highest possible level while keeping them accessible to everyone. If this interests you and you want to support independent science, then please consider subscribing to the Clips channel